we have it 150. Yeah, I'm going to teach you today curvilinear motion, another important motion. In the introduction class itself, we have seen that it is a 2D motion, and when you do not consider a physical geometry of the rigid body, then it is only curvilinear translation. It's called curvilinear translation. There is no rotational effect for a particle mechanics. So now, like you defined your motion parameters, the same motion parameters, how can you look at in this curvilinear motion? So what do you mean by curvilinear motion? Motion is not in a straight line. It is in a curved path. So if you look at vehicle testing is done on a circular track. So the circle is not a straight path. It is a circular path. So that would be described on a ground plane. I refer this X and Y as a ground plane so that you see the ground from the top. So I can put my circle here or any arbitrary curved path. So if this is my curved path over which I have my point P here at any instant is given by its position vector now. What is its position vector? This is its position vector. R vector. So I go to next instant here. This is P dash, and the position vector is again say given by R dash. R dash. So what is position vector? It will give me the coordinate of this point, which is xi plus yj. So where unit vector of x-axis is I and unit vector represent y-axis is j. You know that, right? So this is my position vector. So now change in position, this is delta r vector. So delta r vector is what is r dash vector minus r vector over for the time of delta t. So this is a t. This is a t dash. Delta t is t dash minus t. Then I can define what is my delta r by delta t. This is actually my average velocity, and limit delta t tends to 0. This quantity is going to be simply dr by dt, where that represents velocity vector. So what is the direction of velocity vector? So when delta t tends to 0 means what? It is instantaneous position. So at point P, the velocity is what is instantaneous velocity. So I will represent that velocity by its tangent. So it will be always tangential. So this is my velocity vector V. So this velocity vector also will have two components. I can have like this. So I can resolve this into two components, Vx and Vy. We will do that later. So this is what is I can write. I'll just write it. Vxi plus Vyj is what is my velocity vector. So now, if this is my velocity here, and what would be the velocity at this point at P dash, T dash instant? That would be again tangential there. Velocity direction is always tangential. So this arrow length I have put it same, or I can also have it a larger one. So when I have a longer arrow length, what does that mean? It is accelerated. So the speed along the path is varying. If this arrow length is smaller here than this, that means it's decelerating in the path, you can say. But however, you would have constant velocity, but still it is said to be an accelerated motion. Unlike constant velocity motion, in a rectilinear case, is not an accelerated motion that we have seen. That is static condition. But in the same particle, a rigid body executing its motion in a curved path, if velocity is constant, you cannot conclude that is not accelerated. That's accelerated. That acceleration component is normal component of acceleration. We will see in a while. So, and that is important, necessary to maintain the motion along the path, right? So now this is how I represent my velocities. So now I can define another parameter. What is the acceleration of my particle executing motion? So that is again limit delta t tends to 0, delta v by delta t. So delta v is what here? Delta v here is v vector, that is v dash vector minus v dash vector minus v vector by delta t. So when delta t tends to 0, what will happen? V dash vector becomes this instant one. So it is can be written as an acceleration dv by dt vector, and that's my acceleration vector. I can also have my acceleration component axi plus ayj. So this acceleration vector, where is it located? If you look at in the path, it will be always on the curvature side. So when it has become an instantaneous acceleration point P, I will have my acceleration in this direction somewhere. So this is my acceleration vector, and I will have this acceleration vector. 1 minute. This is my acceleration vector. Whereas I can also resolve this as into two component ax and ay like this. That's what I have written here. Similarly, I can also resolve this velocity into vx and vy. That's what is written here. That is rectangular component of this motion parameters. But definition of motion parameters is what now you have understood. And this acceleration vector of this will always on the curvature side. So what do you mean by curvature side? Since now the path is in this way goes, and your curvature, the center of curvature is somewhere here. So this is its center. So that is defined by its radius of curvature rho. So if you see after this is the point of inflection where this curvature changes its direction. So I will have center here for this when I have to refer this segment of my path. That is by radius of curvature. So now the acceleration vector cannot fall on the other side of that. It will always on the curvature side. That's what is you should always remember. Right? Okay. So if that is so, you have defined now your three motion parameters by vectorially. So acceleration vector is dv by dt, velocity vector is dr by dt, and you could also resolve them for convenient while solving problem in x and y directions like this. So this is what is the description of motion parameter definitions. Using this actual 2D path plane. Along the path, we are looking at any instant t these motion parameters, right? So you have position vector, you have velocity vector, you have acceleration